Okay, the line y equals mx is a tangent to the curve y equals natural log of 2x minus 1 at a point P. Sketch the line and the curve on the same diagram, clearly indicating the point P. All right, so let's grab a pen and let's work out some things, how we're going to sketch this. First, I'd like to know where the log graph lies. So if that's my origin and each of these is 0.25 each line, 0.25, 0.5, 0.75, there's 1 right there, and 0.25, 0.5, 0.75, there's 2, 3, 4, and 5, and 0.25, 0.5, 0.75, there's 1 right there, 0.25, 0.5, 0.75, there's 2 right there. So now I'm going to draw it in. I just need to know where it cuts through the x-axis, where this log graph cuts through the x-axis, the graph of natural log of 2x minus 1. Cuts the x-axis when y is 0, so 0 equals natural log of 2x minus 1. So let's raise both sides, e to the left-hand side and e to the right-hand side. So that's 1 equals 2x minus 1. So 2x is equal to 2, so x equals 1. So it actually cuts through the x-axis at 1. Put a little bit of a cross there. Now, I could quickly draw it in the HSC, but given that I'm wanting to get a nice diagram for my explanation, I'm just going to find a couple of other points, right? So when x equals 2, y equals natural log of 2 times 2 minus 1. So I want the natural log of 3. So I'm going to plot that point, 2, and the natural log of 3 is 1.09, so we're about there. And then when x equals 3, y equals the natural log of 2 times 3 minus 1, so natural log of 5. So you wouldn't need to write all this down in the HSC. In fact, I'm going overboard to try and get a nicer diagram. So that's 1.6, so 0.25, 0.5, about there. Then when x is 4, so you could just not write this down, but just do it in your head. I want natural log of 7. So that's 1.9, so nearly up at 2 there. And when x is 5, I want the natural log of 9. So that's 2.19, maybe there, somewhere like that. And if I wanted to, I could do when it's half. No, because that would be natural log of 0. So at a half, we get an asymptote. So it basically, if that's our asymptote down there, it runs down like that. So there's a quick picture of our y equals natural log of 2x minus 1. But don't waste too much time in HSE getting a picture like that right. So I'm just going to get rid of my working that I used for that, because that was just to get the picture on the page. And we're going to go ahead and try and answer this question. So there we go. Let's pick up a pen again. And away we go. Yep. So we've got the line y equals mx, which is a tangent to that curve at some point P. Now, we want to work out where the point P should be on that graph. Now, if I just grab a different coloured pen here and I draw some random tangent like this light blue one, you can see that, right, it's pretty poor effort, but you can see that it's quite steep and it's going through the x-axis way down there in the negatives, right? So that's y equals something x minus 50 or whatever, right, where it goes through. Now, look at the equation we've got. Y equals mx, right? what is the y-intercept for anything y equals mx? Y equals 2x, or y equals 3x, or y equals 5x. All of them have the y-intercept of 0, the origin. That's right, because there's no plus b or plus c. It's just y equals mx. So clearly where I've drawn my blue one on there, it's not going to be down there anywhere. Same with if I, let's pick one up here and draw the blue one in. The tangent there, well, that's got a y-intercept of 1 point something, right? Well, we want a y-intercept of 0. So I want to find the value roughly so I can draw my picture in such that my point P is, well, what do you think? Somewhere between x being 1, because if x is 1, we get a tangent like this. So that's no good because it goes through negatives. And maybe x equals 4 is the best I can narrow it down to. Maybe x equals 3, although that could go close down to 0. I'm going to say I'm going to test between x equals 1 and x equals 3 to see where the actual tangent is. And I'm feeling, let's get a different colour again. I'm feeling like maybe somewhere around here it may be the right tangent, 2 point something, but that's just a feeling. And I think that would be good enough for them in the HSC to clearly indicate that. But I'm just going to work out fairly precisely where that point should be to make this work out. But I'm going to need a little bit of information. The first thing is the gradient of the curve at any point, right? The gradient of the tangent at any point on the curve is dy dx. Now you can substitute the particular x value in and figure out what that gradient is. So all those different blue lines and the green one I've drawn on the graph have different gradients depending on their x value, and you could substitute the x value in as long as you know dy dx. And I do, because the actual curve is natural log of 2x minus 1, so the derivative is 2 on 2x minus 1. Now you can find that on the formula sheet, the derivative of the function over the function itself for the derivative of a natural logarithm. So that's the gradient of the tangent at any particular point. Now what about the gradient of the tangent from the point of view of y equals mx? Well, from the point of view of y equals mx, if I just draw something over here, it goes through the origin, and maybe this is your particular point you're looking at. It's going to have coordinates x and the y coordinate will be natural log of 2x minus 1. Now this is getting a bit tricky. Why would that be the case? Because this particular line touches the natural log curve. It's a tangent to the curve. So at the point in question, it'll have a y value the same as the y value of the curve, which is natural log of 2x minus 1. So what does that mean for us? Well, we normally would use the gradient is y2 minus y1 on x2 minus x1. But in this case, it'll be natural log of 2x minus 1 minus 0, because origin here is our x1, y1, and whatever value of x we decide to put in, minus 0. In other words, we want to go natural log of 2x minus 1 over x. All right? So I'll summarise that down. From the curve's point of view, the gradient of the tangent is equal to 2 on 2x minus 1. And from the line, the tangent's point of view, the gradient of the tangent is equal to natural log of 2x minus 1 over x. right? This is from the curve's point of view, I guess, and this is from the line's point of view there. So we've got those two bits of information there. Now, perhaps I can make a table and work out some values. So I'm just going to get rid of this stuff here, so I've got room to make a bit of a table. Because this is extra work than I might otherwise need to do in HSC, but I'm trying to explain what's going on. So if I make a table, okay, so over here I'm going to have some x values, and this will be the gradient from the curve's point of view, and this will be the gradient from the line's point of view. And of course, we want them to be the same, right? When they're the same, we'll have a curved tangent that's the same as some y equals mx line that's cranking along. So I've decided from looking at my picture that if I start at, say, 1.5 for x, and maybe go up to 3, I think was probably looking like it's going to be okay. Now let's go in here let's put 2.5, and we may have to go on the other side of 2.5. I don't know yet, I'll have to look. And maybe on this side, say 2.3, 2.7, we'll see. We want to know where they're equal. So I'm just going to substitute into each of these that I've got and find what the different gradients are. So when x is 1.5, from the curve's point of view, it's 2 times 1.5 minus 1. So 2 on 3 minus 1, 2. Oh, it's equal to 1. From the line's point of view, it's the natural log of natural log of 2 divided by 1.5, 0.46. Well, clearly those two gradients are nowhere near each other, right? So let's try at 2. So from the curve's point of view, that's the first asterisk formula. It's 2 on 4 minus 2 on 3. It's 0.6 with the dot. And from the tangent's point of view, 2 times 2 is 4, minus 1 is 3. It's natural log of 3 divided by 2, 0.549. We're getting closer together, but still no good. All right, let's go up to 3. 2 on 6 minus 1, 2 on 5, that gives me 0.4, and 2, 3, 6 minus 1 is 5. Natural log of 5 divided by 3 equals 0.54. Okay, let's try 2.7. So 2 on, and I get 0.45, and 2.7, natural log of 4.4 divided by 2.7, 0.54. Okay, let's go back to 2.5. So that's half, and that's lateral log of 4 divided by 2.5, and I get 0.55. So you can see that I'm starting to get closest to it, and I think 2.3 is looking pretty good. That's 2 on 3.6. That's 0.55, and natural log of 3.6 divided by 2.3, 0.55. Okay, so I can see they're both the same when x equals 2.3. So after that effort, right, which is not going to get you any more marks in the HSC, but I'm just trying to explain better here. Oh dear. After that effort, let's just draw in the rest of this line again. Let's just draw in the rest of this logarithmic curve that I erased, and we'll get another colour and draw in our tangent at 2.3. So about there. That is where it just touches. Okay, so that's clearly our point P. Right, so, you know, in order to figure out exactly where the point P is, they would be wanting us to solve 2 on 2x minus 1 is equal to the natural log of 2x minus 1 on x, all right? That's what they'd be wanting us to solve. And I think that's quite a difficult equation to be trying to solve. So clearly they're not wanting an exact answer on this. They're just wanting you to be able to get P in roughly the right position. And I've done a lot of time on that, but you could have done that quite quickly with some intuitive quick guessing on the calculator. So I've got a nice picture going there, and I'm going to go and answer the next question. So the next question is, show that the coordinates of P are 2 plus m on 2m and 2 plus m on 2. All right. So once again, we can look at the coordinates of P from two different points of view. We can look at it from the point of view that this is the point X. It's on the curve, but on the tangent, it's X, mx, because y equals mx. And on the curve, the coordinates are x and natural log of 2x minus 1. All right, so it just depends the point of view, but mx and a natural log of 2x minus 1 are the same thing at that particular point. And because it's a particular point, might be nice to say, let's call it capital X, just to indicate at this particular point X that this is the case. So I'm just going to change that there. And now I'm going to go and have a look at answering this next question down here. The next question is saying, show that the coordinates of P are that. Well, I know that the gradient m is equal to the dy dx on the natural log graph, because that's what the gradient of the curve, the tangent to the curve, is at any point. So that was 2 on 2x minus 1. So at that particular point x, right? At the particular point x. And that means I can say, well, that means that 2x minus 1 is equal to 2 on m. So 2x is equal to 2 on m plus 1. So x is equal to 2 on m plus 1 on 2. And if I sort that out, make that look a bit nicer, x is equal to 2 on m plus m on 2 equals 2 plus m on 2, which is 2 plus m on 2m, which I hope is what they've got. Let's have a look. 2 plus m on 2m, yeah. Now, that comes from the gradient of the tangent, y equals mx, being m, and the gradient of the curve, you differentiate the natural log graph, and of course they're the same thing at that particular point, capital X, capital Y. Now, I know that from what I've written above, that particular point P has got the following coordinates. It's got x and mx as its coordinates from the point of view of the line, but it's also, as I wrote above, it's got the coordinates x and natural log of 2x minus 1 from the point of view of the curve. Same coordinates, just sort of looking at it from different points of view. So you would choose the appropriate one. I know what x is, I just worked it out. I just worked out what the x value is here, right? That x is equal to 2 plus m on 2m. And so now I need to take this up here, 2 plus m on 2m, right? X is 2 plus m on 2m. And I need to decide which version I'm going to use. Well, look at the answer that they're after. Are they wanting anything with natural logs and things hanging around? No, they're not. So it's looking like I'm going to use this version up here. X, m times x is the x and y coordinates. Now x is 2 plus m on 2m. So m times x is m times 2 plus m on 2m. Right, so this here will be m 2 plus m on 2m. The m's cancel and you get 2 plus m on 2. So I think a satisfactory explanation in the HSC would be that the gradients of the line and the gradient of the curve are equal, and you'd get your first point. And your second point, you could write down what I've written down here with an asterisk there, and then substitute in, and away you go. So that's why those coordinates are that. But they're also, you know, this wouldn't be the answer, but I'm just saying they could have said, show that the coordinates are, and show that the coordinates are 2 plus m on 2m and the natural log of 2 times 2 plus m on 2m minus 1. They could legitimately have said, show that it's some version of that. I mean, that was, right? That would cancel down and you might be able to make it look a bit better. But that is also relevant. But it's just not what they asked. They were just asking for the show that the coordinates of P are given in that way. So I'm going to now remove this because that's not the point of view they were after in this question, and that was not what they were after. They were simply after it from the tangent line's point of view. All right, finally, hence show that 2 plus m is equal to the natural log of 4 on m squared. Oh, well, here we are. So the point P, the point P has coordinates x and natural log of 2x minus 1. It does have those coordinates. So, and it also, or P is x and mx, right? So therefore, mx is equal to the natural log of 2x minus 1, right? Capital X. It's only happening at that particular point. So I could give those coordinates in those two different ways. Now, the x that we've worked out above was 2 plus m on 2m. So m, 2 plus m on 2m, is equal to natural log of 2 plus m on 2m minus 1. Okay. 2 plus m on 2 is equal to natural log of 2 plus m on m minus 1. And now we just need to sort that out to get what they're after. So let's just 2 plus m on 2 equals natural log of 2 plus m on m minus m on m. So 2 plus m on 2 equals natural log 2 plus m minus m on m. So 2 plus m on 2 equals natural log of 2 over m. Now I'm getting very close. They're wanting something with a 4 on the top and an m squared on the bottom and only a 2 plus m on that side. So clearly I need to, on the left-hand side, just get 2 plus m. So I'm going to need to go down a couple of lines here. All right, so let's times both sides by 2. Now we've got the left side looking like we need to. So now let's use that rule with logs that says if there's a number out the front, it comes up and becomes a power. And then let's actually square that fraction. So 2 squared on m squared. So 2 plus m equals natural log of 4 on m squared. Just go and check if that's what they wanted. Yeah, so they wanted us to look at the point from those two different points of view.